So circular functions, just like the unit circle itself, there's a few things that we can pick up from that to help us as we try to find values for sine and cosine and even tangent at sometimes. So when we've got a terminal side of an angle and it intersects our unit circle, which it will somewhere, because again it's going to be circular in nature, then my cosine of theta equals my x value, and my sine of theta equals y. In other words, when I'm moving my way around the unit circle, if I have a certain particular degree measure and I can find values for x and y at that point, which I can, because we talked a little about that when we were getting into some of the unit circle yesterday. So like for instance, if I know it, I'm at 120 or 2 pi over 3 degrees, this will be my cosine value, this will be my sine value. I can get values that way from this. So that's going to be my big thing that I want to focus in on as we're doing these. That whatever that x value coordinate is actually my cosine theta value, and the y value is actually my sine theta value. But here's the real kicker. I can even use that information to find my tangent. My tangent is just going to be sine over cosine. Or if I want to simplify it, I could also say the tangent of theta is just going to be y over x, whatever those values are. Because sometimes they'll just give me the straight values. That might be easier to think about than just thinking about it as sine over cosine. And we're going to play with these a bit, and I know in some of the directions it's going to say just to find sine and cosine, but we're going to find tangent too, just so you can see how this works. So in this first example, the terminal side of our angle intersects the unit circle at negative 5/6 square root of 11 over 6. All that means for us is that this is my cosine value at that particular angle measure, and this would be my sine value. So I could even use this if I wanted to figure out what the angle measure itself was. But that's all I'm doing. I'm strictly taking my x value, it's cosine, my y value is sine, and that's all there really is to it. There's that direct correlation. So when it's asking me to find cosine and sine on these, all I'm basically doing every single time is going, okay, cosine is just the x value, and my sine value is going to be the y. And there's lots of things I could figure out from this. For instance, I see that cosine's negative and sine is positive, so it'd be fairly simple for me to see, ooh, this is going to be somewhere in the fourth quadrant. And I could figure that out from there, or I could actually look at my unit circle and come up with the same thing. But let me ask this. What if I asked you to find the tangent of theta at that same place? Because we noted up top it would just be sine divided by cosine. Another way of looking at it, if you do sine divided by cosine, and I'll do it completely out once, and then we'll start figuring out where the shortcut's going to come. If I do sine divided by cosine, when I go to take the reciprocal of my second fraction, the twos are going to cancel out. But I'd still have this little issue because I can't have that radical in the denominator. So I'd have to rationalize it by multiplying both the numerator and denominator by the square root of 3. So my tangent of theta would actually end up being negative square root of 3 over 3. So basically what will happen for you on all of these is that these are going to cancel out each time, so you don't have to necessarily write all that out. You can just look at that second one's reciprocal, and it's going to go into the denominator. So, to stay normal for one more, I'm going to shift to the right instead of shifting down and say, okay, so you're saying cosine's always going to be my x value. Oops, forget my negative. sine is always going to be my y, which is true. So the tangent then, again, when I start thinking about it as far as these go, I'm like, okay, sine over cosine. That's going to flip, and I'm going to end up with the square root of 5 over negative 2. So you're like, okay, so basically what you're getting us into is you're going to have sine's numerator over cosine's numerator is basically what my tangent's going to be. Yes. And the only time I have to do anything else with that is, of course, if, like we did over here, we've got a radical that we need to get fixed up, get situated a little. But there will be some strange little turns. For instance, number 2, 0, negative 1. Now let me come back up here to the top for a second. We only talked about this a little bit yesterday, but at each of my axes, my 90, 180, 270, 0/360, I use those points to try and figure out the values. So at 0, 1, it's still going to be my cosine and my sine. And then my tangent is still going to be sine over cosine, but oops, I can't divide by 0. So that would be undefined. And typically with these, it's just going to be the base 3 functions that we're looking to find. We're not going to do a whole lot of figuring out cotangent and secant quite as much with these, or even cosecant as we do the basic 3 trig functions. So any issues here at the start when we're given the coordinate, because that's, again, as you can see, is just going to kind of be the first part of this. As long as we can keep that tangent part straight, we'll be all right. All right. So then next, they may give us where the terminal side is. So they're going to give us the angle, but then we've either got to use our knowledge of the unit circle or yank out the unit circle to help us out. So for instance here, they mention that P is on the terminal side of 45 degrees. So if I'm still playing here, and it's all right if we are, I find my 45 degrees, and I notice that my cosine and sine are each square root of 2 over 2. They're both in the first quadrant. So I go, okay, so the cosine is going to be square root of 2 over 2. The sine is also square root of 2 over 2. And like I said, as we keep playing with these, with your unit circle, you'll find it easier and easier to just rattle these off, and then we can figure out the rest from there. So if I were asking you to find your tangent then, remember, like we said before, it's basically going to be numerator of sine over numerator of cosine. And when you divide something by itself, you just get 1. But that's what we're kind of looking at. But again, it comes back to getting used to how this is going to work. Now, I do on these next couple want to get you thinking about the positives and negatives a little bit more. So I'm going to sketch a picture here. I don't have to break out my protractor and be perfect with this. But I realize 120, when I think about its terminal side, is going to get me into quadrant 2, where only sine is going to be positive. So again, like we'd mentioned yesterday, when I'm at 120, pull this back up. When we're looking at these, I said, oh yeah, my reference angle then would be 60 on this. So I'd have my cosine and my sine values, except my sine's going to be positive and my cosine isn't. So here, my cosine would be the same as that reference angle, the 1/2, except for the fact that it's negative. My sine of theta for this would be the square root of 3 over 2. But it's in its positive quadrant, so it's going to stay positive. And again, as you're trying to remember your unit circle, the big things, like I said, if you don't memorize every single degree measure with how it goes, if you know these three, you can always use a reference angle and then just play with the signs based on what quadrant they're going to be in. That'll pop back up again here in a bit. So then my tangent would be my sine over my cosine. Or you could just write it as the negative square root of 3. And we want to always be exact with our answers when we're doing this. So this isn't one of those where I want to put like 0.5, negative 1.73, 0.8660. Please, please, please stay with the radicals when you're doing these. It's just a little more sensible for what we're doing. So for now at least, so we can keep referencing and using those reference angles, I'm going to just keep reminding myself, okay, terminal side's at 240. I need to get back to 180. So my reference angle would be 60. And I go, all students take. Ooh, just tangent's going to be positive, okay. So I remind myself again, say, okay, so the cosine of theta with my reference angle being 60 is going to be 1/2, but again, it's going to be negative. My sine of theta, where the reference angle is 60, is going to be square root of 3 over 2, but it's also negative. And now you begin to see how these can both be negative and I can still get a positive tangent value, because when I go to do the tangent, negative square root of 3 over negative 1 gives me a positive square root of 3 because I'm in quadrant 3 with my terminal side. So again, it's not necessary with your unit circle. You do want to know your radian measures, okay? Going with your 30 and your 45 and your 60 in each quadrant. You do. But as long as you've got the basics, we can just kind of use our signs to help us. And then the same in this last one. 90, 180, 270. Here's my 330. My reference angle gets me back to 360, which means my reference would be 30 degrees. So then I've just got to remember, when I have that 30 degree reference angle, that my cosine is square root of 3 over 2. Sine and cosine flip when we go from 30 to 60. They switch with each other, I should say. I don't want it to sound like they're reciprocals. All students take calculus, so cosine's positive. My sine's going to be 1/2. But we're not in sine's favorite quadrant, so we get negative. And then my tangent, numerator of sine, numerator of cosine, and then I want to go ahead and take care of that because I don't want my square root down here, so we'll rationalize it and get my tangent. Any issues there? Again, so you can kind of see where my unit circle info is starting to combine with what we're doing with reference angles and things like that to try and simplify things a little bit. Now we're going to start kind of introing towards the next portion of this. So any issues before we flip over to the back? No, just B. Right. So when we hit the back, we're just going to take a look at what's called a periodic function. It means we've got y values that are going to repeat at regular intervals. You're going to see lots of patterns when we're doing this, lots of curves. So a complete pattern is called a cycle. So where we start, we keep the pattern going until we get to that same point again, and that's my period. The horizontal length of one cycle is called the period. So when I'm looking through these, what I'm going to do is I'm going to look to see where does my, oops, I've dotted the wrong place. That figures. Where does my particular graph start? And then I look to see, okay, where does the pattern seem to break up and start over? And it seems to keep starting over as I go through here. It goes up, it curves down, and then it gets back to 0, and it goes up, and it curves down. And I'm looking for that same pattern over and over. And wherever that pattern starts and stops tells me what my period's going to be. So in this case, between 0 and 10, it does the same thing as it does between 10 and 20, between what it does between 10 and 30, and so on forever. So that's what I'm looking for when I look for a period. And this will help us when we start graphing our trig functions. So I look here on this first one and I go, okay, it starts here. Where does it start over again? Looks like it starts over again here, because it looks like that first step's always going to be this quick little horizontal line. So between here and here would be what I'd be looking for. But here's one thing I'm going to start getting you used to. You're like, oh, okay, so it's like 2.5 pi. But when we're talking about cycles, especially when radians, when pi gets involved, we're always going to talk in improper fractions. So this is a period of 5 pi over 2. Because what you'll start to find as we do this is, for instance, between 0 and 1 is 1/2, right? So this first one would have been pi over 2. Between 1 and 2, 1.5. But again, we're looking at improper, 3 pi over 2. And you might even see another pattern start to develop. 1 pi over 2, 2 pi over 2, because 2 over 2 is 1, 3 pi over 2, 4 pi over 2, because 4 over 2 is 2, and you could actually just run that pattern to know what the rest of them would be. But for our purpose, that's where this one happens to end, so it's going to be 5 pi over 2. So then, when I get down to 10, I'm kind of playing the same game here. So it looks like we're starting here. Where does it look like we start over again? Because I notice if I do my V, when I start here, I do the V again. So I'd go between here, and my period would be 6. Okay, so I've got to really look for where that pattern starts and where it stops. Now, if on that one, the arrow at the end may have confused you, there's another way I could have looked at this one. I could have said, I'm starting down here at the bottom. Okay, this one starts down at the bottom again. Here's 3. Here's 9. Between 3 and 9, it'd also be 6. So as long as you can find that pattern somewhere, you can go ahead and use your cutoff that way. What about 11? 4. Start here. Start over again here. My period would be 4. Now, 12, I have to admit, this was not a smart idea on my behalf because we have an issue. Like, what's the issue? Well, let's see. Well, be quiet. What do some of you possibly think it might be on this one?
I think it's 2.
I think it's 2. Okay, let's see. So if we started here and ended here. Now see, I'm with you. Over, up, over, start over, start over. I think this is good. Because I was talking with Mrs. Hoffbauer about this one. And we're like, well, is that actually a function? Because I don't actually see that same one happen at the end. But if it keeps going, you could cut it off at that point. So I agree with you. So that one would be good there. Then we get into an actual curve that might look like what we're doing. 13. 2 pi. Because that's more of what we're going to be looking at over the next few days. Looking at these sine and cosine and tangent curves, or sometimes not curves, is a small hint of how these are going to be working. So, here's the last thing we're going to kind of take a peek at here. We're going to look for some exact values of our functions. This can get a little more interesting because we don't have 855 degrees on our unit circle. We basically do one rotation around a 360 and then we're stuck. So what am I supposed to do in a case like this? If you remember back a little bit, we talked before about something where you could add or subtract 360 degrees to try and find a similar angle that has similar characteristics. So now what we're going to do is we're going to get this and we're going to try to get back down into that area between 0 and 360. So what I'm going to do is I'm going to keep subtracting 360 from this until I get myself back into a degree range that's workable for me. So I'm going to be looking for the sine of 135 degrees. Okay, I got this. If I think about it for a minute, sketch if I must. If this is 135 degrees, my nearest x-axis would be 180. So my reference angle is 45. So I need the sine of 45 degrees, which is the square root of 2 over 2 from my unit circle. And since I'm in the second quadrant where sine is positive, I get my answer. So occasionally, if I get myself into a dilemma, even if they're in radians, and some of you may say, can I put it back into degrees and then finish it that way? You can, but remember, if it starts in radians, it needs to end in radians. So for instance, if I didn't see all of this down here already, I'd say, okay, I need to keep subtracting 2 pi from this until, because that's 360, until I get down into a range I need. Well, that's not going to help me when it's over 6. So I'm going to be subtracting 12 pi over 6, because that's its equivalent. So if I started doing that, because the example I copied off here doesn't quite show all of this, you're like 19 pi over 6. Let's see. No, because 12 pi is a whole circle, so that's not going to work yet. And here's where the 7 pi over 6 that they're playing with is coming from. So then you sit for a minute, you go 7 pi over 6. Oh gosh, Harty, I can't remember the degree measure on this. And that's when, again, for now, if you need to come back over to a unit circle and say 7 pi over 6, that's 210 degrees. Okay, I need to remind myself of that for a minute. 210 degrees, it's going to be over here somewhere. I need to get back to the x-axis. My reference angle is 30. Which is square root of 3 over 2 for cosine, but all students take, that's where the negative's coming from, because I'm not in cosine's one of their 2 quadrants. So it's just going to keep coming back to reference angles. Those 3 basic ones, keep popping this up here enough. You know those, you know your 4 quadrants, life is simple, because you can do everything with those. So again, when I'm looking for exact values, oops, over 360, add 360 back to it. You're like, oh crap, it's still negative, Harty. Not a problem. Negative 150, all I need is to think, oh yeah, 90, 150, here's negative 180. It's 30 degrees. 30 degrees is my reference angle. So sine of 30 is a half, but all students take, that's not sine's quadrant. So it can become a little bit of work. 495, too much. Cosine of 135. I go, okay, 90, second quadrant. Second quadrant, reference angle's going to be 45. So let's see here. Cosine 45 is square root of 2 over 2. But am I going to be in the right place in number 2? All students. Nope, that's sines. Negative. Ooh, let's see what else we got here. Negative 5 pi over 2. Negative 450. Nope, that's too much again. You're like, now wait a minute. Before you did 12 pi over 6, now you're doing 4 pi over 2. Remember, it's 2 pi that I'm adding or subtracting, because that's what 360 degrees is. So I use my common denominator. Before it was 6, now it's 2. 4 divided by 2 would be 2. So negative pi over 2 is what I'm looking for the cosine of. Negative 45, that makes a difference, remember, because negative 45 will come down here. My reference angle will still be 45. So the cosine of 45 I'm just looking at this for a minute to make sure I didn't do something silly. Harty. Pi is 180. I made it 90 for a minute. I made up my new math. I am not allowed to make up new math. Oh dear. Negative 90 degrees. Ooh, that's a different problem. My apologies for those of you that were following along with me. I was waiting for somebody to holler at me here. Negative 90 degrees. Now that's a little different of an issue, like we were saying. That one, remember, I've got it 0, negative 1. Which one of those values is my cosine value? The 0 or the negative 1? The 0. So if I end up on an axis, whichever, always going to be cosine, always going to be sine. Just depends on which one I get. Speaking of, sine here, this is sine of 300. You're like, how do you know that again? 5 times 180 is 900, divided by 3 is 300, so I don't have to add or subtract anything this time. 300. 70. There's my 300. But I've got 60 more to get back to the axis. So the sine of 60 is square root of 3 over 2. All students take calculus. It becomes negative. This is going to be one of those assignments that at the beginning you're going to probably be looking at the circle and looking at a cheat sheet a lot. By the end you're going to be snapping them because you're going to be like, you're doing them so much you're not even going to think about it. So this guy down here, this bookwork, make sure I do this right. Yes, homework check 11, number 2, because the assignment we did yesterday was number 1. So number 2 on there, and then tomorrow we start playing with graphs some on this, which is a little more interesting. At least to me it is.